So, welcome to the lecture on mathematical modeling. In this lecture, we will discuss on electrical system. So, as in previous two lectures, we learned how to model mechanical systems, translational as well as rotational systems. In this lecture, we deal with electrical systems. So, we know that electrical systems, the basic elements are resistance, inductance or inductor and capacitor. So, these systems can be modeled using these elements, and we applied mechanical system we applied Newton's law to write the differential equation of the system. In electrical systems we use Kirchhoff's law, Kirchhoff's two laws, that is current law or node law and voltage law or loop law. So, what is current law? So, here the current law tells that the algebraic sum of all currents entering and leaving a node is 0, or the sum of currents entering a node is equal to the sum of currents leaving the same node. So, if we have some electrical circuit and there is some point in the electrical circuit and there are currents coming like I1, I2 and these currents leaving here I3, I4. So, according to this current law, the currents entering to this node is equal to currents leaving. So, I1 plus I2 equal to I3 plus I4. So, let us say if we have some point where current I is entering and then here is I1, I2. So, here I equal to I1 plus I2. So, this is the current law. Now, the voltage law or loop law tells that at any instant the algebraic sum of the voltage around any loop in electrical circuit is 0, or the sum of voltage drops is equal to the sum of voltage rise around a loop. So, this voltage law is applicable for a loop, that if in any loop we traverse through the loop and we sum the voltages with their signs, that will be 0, or if there is some voltage drop and voltage rise, so the voltage drops is equal to voltage rise around the loop. So, a mathematical model of an electrical circuit can be obtained by applying one or both of Kirchhoff's law. So, we will see that how we can get the mathematical model for a basic electrical system that comprise three components: resistance, inductor and capacitor, and how can we find the transfer function of an electrical system. So, let us take an LRC circuit. So, here we have this circuit, this is inductor, this is resistance and this is capacitor, and here we are measuring the output voltage. and there is a current I t. So here is this input voltage, this is output voltage we are measuring around the capacitor. So this is output voltage we are measuring around the capacitor. And so we want to write the mathematical model for this system and to find the transfer function of this system. So we should try to understand that the voltage, we can write voltage drop in the inductor L di by dt. In a resistor, voltage is proportional to the resistance, and in a capacitor it is 1 by C I dt. So let's traverse this. We apply the, because this current I is flowing through this loop, there is no any diversion of this current. So this same current is flowing through this loop, so we don't need to apply the, I mean, node law, but we apply the voltage law. So voltage law we apply. So according to the voltage law, we traverse through this loop, we do the algebraic sum of the voltages, drop and rise, and then that is equal to 0. So voltage drop across the inductor is L di by dt, across the resistor is IR, and across the capacitor is 1 by C I dt. So this is the voltage drop, that should be equal to voltage gain. So here this is a source, so we are have a voltage gain EI t. Now here this is output, we are measuring here output. So output is equal to 1 by C I dt. So output we are taking the voltage across the capacitor. So now we can see this is the equation for this system. It contains integration as well as differential term. Now we have to find the transfer function. For this we take the Laplace transform. So we take the Laplace transform of this equation number 1. So we will get Ls Is plus R Is. Here I is function of time, because this current changes with time when the voltage changes with time. And here is 1 by C, this is integral. So 1 by S into Is, because the Laplace of integral is 1 by S Is, and that will be equal to EIS for this equation 2 we can write EOS equal to 1 by CS IS. Now the transfer function EO S by EIS So 1 by Cs Is upon Ls Is plus R Is plus 1 by Cs Is. So this we can write 1 by Cs upon Ls plus R plus 1 by Cs. So here again we can simplify this expression. We take L here and S here. So S square plus R by L S plus 1 by LC. So we can represent this transfer function. So here EIS and EOS, and this is 1 by LC S square plus R by L S plus 1 by LC. Again we see that this is the transfer function that contains the properties parameters of the system, that is L, R and C, and this is again the second order system because here there is a square term. Now we discuss the concept of impedance in case of electrical circuit. In electrical systems, the concept of impedance can be used to find the transfer function and represent the system. So in electrical system, the impedance is defined as voltage upon current in S domain. So for inductor L, where V t equal to L di dt. So here Vs equal to L into S Is. So here Vs upon Is equal to Ls. So this is the impedance for inductor. For a resistance, V equal to I R. So here V S equal to R into Is. So Vs upon Is equal to R. Similarly, for a capacitor, we have V equal to 1 upon C I dt. So Vs equal to 1 by Cs Is. So this implies that Vs by Is equal to 1 upon Cs. So in this slide we can see we have represented the impedance. So voltage current relationship for these three elements, capacitor, resistor and inductor, current voltage relationship, and then voltage charge relationship, and then impedance. So impedance is Vs upon Is. So for capacitor it is 1 by Cs, for resistor it is R, and for inductor it is Ls. Now we can find this system we can represent as equivalent impedance form. So, here we have, let us say this is Z1 impedance, and then here Z2, so here EOS, EIS, and this is Z1, that is of course function of S, and because impedance is defined in terms of S. Now here Z1 equal to, that is impedance of a inductor and impedance of resistor. So, that is Ls plus R, and Z2 equal to impedance of the capacitor, and that is 1 by Cs. So, here we can find from here EOS by EIS equal to Z2 as Z2 upon Z1 plus Z2. Z2 upon Z1 plus Z2. So, Z2 is 1 by Cs and Z1 is Ls plus R, and Z2 is 1 by Cs. So, we can again simplify it 1 by Lc and S square plus R by Ls plus 1 by Lc. So, we can see that using the impedance method we can also find the transfer function, the same, we can see we find the same transfer function. So, therefore, this method is important for the systems. We do not need to go to the differential equations, we can directly find the transfer function. So, we can take one more example, and that may contain the nodes where the currents will divide, and so it may form the more than one loop. Okay, so here we have R1 to R2, two resistor and two capacitors. There are two loops here, and we are reading the output here across this second capacitor. Now, let us represent it in the impedance form. So, here we have EIS, then we have current I here, of course it is function of S, then here Z1 impedance, this is, here we have capacitor impedance, then here one more capacitor impedance. And this is EOS. So output voltage. Now if we have current I, this current will be divided at this node. Let's say this is I1 and this is I2. So here we have node law, that is I equal to I1 plus I2. We can apply the node law. And then this voltage, so we go this loop. So Z3 I2 plus Z4 I2, and here minus Z2 I1 equal to 0, because here we are going in the direction of current and here we are going opposite to the direction of current. So here minus Z2 I1. So Z3 plus Z4 I2 equal to Z2 I1. So we have this equation number 1 and equation number 2. From the two equations we can find I1 and I2. So we can find I1, I2. So we solve these equations, we will find I1 equal to Z3 plus Z4 upon Z2 plus Z3 plus Z4 into I, and I2 equal to Z2 upon Z2 plus Z3 plus Z4 into I. Now EIS, this first loop, so EIS equal to Z1 into I plus Z2 into I1, because there is the voltage drop and here is the voltage gain. So this, now we can put here this Z1 plus Z2, I1 we can represent in terms of I, so Z3 plus Z4 upon Z2 plus Z3 plus Z4 I, and EOS equal to Z4 into I2 equal to Z4 into I2. So here Z4 into Z2 upon Z2 plus Z3 plus Z4 into I. Now we can find EOS by EIS. So EOS we can divide this term by this term. So I will be cancelled out, and these terms, so Z1 we can put, so this is equation number 3 and this is equation 4. So EOS by EIS we can find by dividing equation number 4 by 3, this term, the right hand side terms, and there we could put Z1. So Z1 is a resistor, so the impedance is R1. Z2 is a capacitor, so its impedance is 1 by Cs, and Z3 is a resistor, so its impedance is R2, and Z4 is again a capacitor. It's so here is C1 and this is C2, and by putting these values on these impedances we can find the transfer function UAS by EIS. So these examples are taken from the book of Norman S. Nice, Control Systems Engineering. So we learned that how to model the electrical systems. We use the basic elements like resistance, capacitor, and inductor, and we can go apply two methods. The differential, first we write differential equations using the Kirchhoff's law, and then we find the transfer function by taking the Laplace transform of that equation. Second method is that we represent the circuit in terms of impedance, circuit impedance, and we can directly apply these laws on the impedances, and we don't need to write the differential equations in this case. We can directly find the transfer function. So I thank you for attending this lecture, and see you in next lectures. Thank you.